right, today we're going to begin our study of the derivative. Chapter 2 is all about limits, behavior of the graph, but it did begin with this concept of average velocity versus instantaneous velocity. And we're going to see how that applies to the derivative as we move through this chapter. So as a warm-up, I want you to take a moment to find the equation of the line that passes through the point 2, 3 and has a slope of -2. And remember, I had suggested using point-slope form of a line. So try to get more and more comfortable with that as we move through this chapter in particular. Okay, with point-slope form of a line, as long as you're given those two criteria, you just have to plug those in. So y minus 3 is equal to -2 times x minus 2. And throughout this entire year, you can absolutely leave your answer in point-slope form. There's no need to change forms. So again, we need a point, we need a slope, and we need the line. We'll follow this throughout this chapter and beyond this year, so the more comfortable you get with it now, the easier it will become in the future. All right, so with the beginning of our study of differentiation, okay, keyword here, differentiation is implying the derivative. Okay, so there are three ways to think about the derivative. One is a rate of change. Two is the slope of a tangent line to a curve. And three is the limit of a difference quotient. So today, as we learn about it, we're going to use the limit of a difference quotient. You may or may have not seen this at the end of pre-calc last year. But as we move through the chapter, we'll talk about it as a rate of change, and we'll also talk about it as the slope of a tangent line to a curve pretty often. So our goal here, like it was when we were comparing average velocity with instantaneous velocity, right now the way this line is sketched is we have a secant line. We have 2 points passing through a curve, points P and Q, which I could find the slope of, and that would in turn give me the average velocity. But the study of the derivative says, well, can we move those 2 points, P and Q, closer and closer together, creating delta x and delta y of 0? Okay. Our goal is to create a tangent line with 2 points. Okay. So our delta x is approaching the difference between x minus a, we're taking that to 0, and our delta f is also going to be approaching 0. Okay, so, and for your notes here, definition, the derivative of f of x at x is equal to a is the limit of the difference quotients if it exists. Okay, there's going to be two different ways that we can use this. Method 1, Method 2. And today during this study, we'll be looking at the derivative at a moment, at a specific point. And in the future, we'll be able to also find the derivative as a function. So if we look at this f prime of a, that notation, that's how we would read that, f prime, that's equal to the derivative. That's how we notate to find the derivative. It equals the limit as h approaches 0 of the quotient f of a plus h minus f of a divided by h, right? And if we did direct substitution right off the bat, we are creating the 0 over 0. We are purposely creating an indeterminate form. Okay? Now, we learned last chapter that an indeterminate form of 0 over 0 always implies that we will be able to manipulate this and cancel out that 0 over 0 factor. So this is also equivalent to the slope of the tangent line and the instantaneous velocity. Okay. When the limit exists, we say that f is differentiable at x equals a, and an equivalent definition of the derivative, f prime of a is equal to the limit as x approaches a, right? If those two values become the same value, then f of x minus f of a, change in y over change in x. But again, we are forcing that 0 over 0. If a limit is said to be indeterminate, right, if the quotient is indeterminate, it is always possible to algebraically manipulate it and find an answer. Okay, so our first example. It won't tell you which limit definition to use, so we'll just kind of go back and forth and get comfortable with both of them. So use the limit definition of the derivative to compute f prime of 3, where f of x is equal to x squared minus 8x. So for this one, we're going to use the first limit definition. So f prime of 3. Okay. Everywhere there was an x, we're replacing it with 3. The h's will stay for now. So equals the limit as h goes to 0 of f of x plus h, or 3 plus h, minus f of x, or f of 3, divided by h. Okay. Now this is showing us our function input, right? So the function is defined as x squared minus 8 times x. So now the numerator needs to change to show the actual function. Limit as h approaches 0 of big parentheses, quantity 3 plus h squared minus 8 times parentheses, 3 plus h, close big parentheses, minus parentheses, 3 squared minus 8 times 3, all divided by h. So we still have on the left here f of 3 plus h, and on the right f of 3. So now our job is to expand this really carefully with our algebra skills and simplify combining like terms. When you do these problems correctly, all of the non-h terms in the numerator should cancel each other out. Okay? We're looking for that indeterminate factor, and in this case, we're looking for an h over h to cancel out. Okay, so I'm foiling the 3 plus h. So that would give us 9 plus 6h plus h squared. Remember, 3 plus h times 3 plus h. First, outer, inner, last. That's where that's coming from. Okay. Minus, we have parentheses here, so minus 24 minus 8h. Okay, and then that last one, minus a quantity. Inside those parentheses, 3 squared is 9. 9 minus 24 would be a negative 15. So we have minus negative 15, or plus 15. Okay. All over h. Okay, checking out what cancels. We have a 9 minus 24 plus 15. So all of those would add to 0. And every remaining term does have an h in there, which means that I get to factor an h out of the numerator, leaving me with 6 plus h minus 8. Okay. Divided by h. Now that I have the h's pulled out, I can cancel them. That numerator, 6 plus h minus 8, simplifies to h minus 2. And now I still just have to evaluate the limit. So now that I've canceled out the indeterminate form, I can plug the 0 in. 0 minus 2 would give me a final answer of negative 2. Okay, so what's the graphical connection? I want you to always think about this. We started to do this a lot in Chapter 2, but in Chapter 3, we're really going to be analyzing our graphical connection. So we think about the original function, x squared minus 8x. If I graphed it relatively accurately, I would have x-intercepts at 0 and at 8. Okay. At 3 is where we are looking to find the derivative. So roughly here. All right, I know it's to the left of the vertex. The answer that we got, negative 2, stands for the slope of the tangent line. So if I sketched a tangent line, of course I'm not going to know exactly if I'm correct, but at least I can look and say, yes, I have a negative line sketched, and I got a negative result. So that connects, that's correct. Okay, let's try another example. I want you to give this one a try using the same same definition that we just used. So practice it one more time. Okay, pause this video, do it yourself, and then check back in. So remembering that this is f prime of a technically. Okay. So f prime of 1 is equal to limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. When we input those into our function, x squared plus 1, we're going to have the limit as h approaches 0 of 1 plus h squared plus 1 minus 1 squared plus 1 all over h. Foiling, simplifying, combining like terms. Limit as h goes to 0. 1 plus 2h plus h squared plus 1 minus 2 all over h. Those constants, 1 plus 1 minus 2, give me a 0. In the numerator, I can factor out an h, and I'm left with 2 plus h. Divide out those h's, and then input the 0, so I get an answer of 2. Okay, in this case, graphical connection, x squared plus 1 would be here. At 1, the tangent line would be a positive tangent line. Okay. So the next step from here, now that we know how to find the derivative at a particular x value, we can find the equation of the tangent line to the curve at that point. So this is the exact example that we just did. We found the derivative at 1 of x squared plus 1, and that came out to be 2. Okay, so if we want an equation of a tangent line, you're always going to structure your work as point, slope, line. Okay, the point is always coming from the original function. It is on the curve. So the notation for that would be a comma f of a. The slope is always the derivative. So that is f prime of a. And the line is always going to be y minus y1 equals m times x minus x1. Now remember, our derivative is a slope. Our a comma f of a is a point. So I can rewrite my line equation and make it appear like a calculus instead. Y minus f of a equals f prime of a times x minus a. Okay, it's saying the same exact thing. So we've done most of this work already. We already know that the derivative at 1 is equal to 2. We know our a value is 2, and actually in that limit definition, we found f of a. Right? We found f of a by plugging it into x squared plus 1 in the numerator. And we got back out, I'm sorry, this should say 1 here. We got back out 2. So our ordered pair is 1 comma 2. So now we take both of those pieces and we put them into our line. Y minus 2 equals 2 times x minus 1. And I could graph that, and it would give me exactly this line. Okay. Okay, let's take a look at an example that has a rational function. So my first step is asking you to sketch the graph of f of x equals 1 over x and the tangent line at x equals 2, just to get a quick visual to begin with. Okay. These graphs do not have to be perfect, but if you need help graphing, you can certainly use your calculator or Desmos. The graph of 1 over x has horizontal and vertical asymptotes at 0, and the two branches are bounded in the first and the third quadrants. So our tangent line at 2 over here. Relatively flat, but it's negative. Okay, so let's see. The reason I'm having you sketch this is because we can really think about what our output should be. So based on the sketch, do you expect f prime of 2 to be positive or negative? So negative. Okay, find an equation of the tangent line at 2. So the first thing we need to do is find our slope using the limit definition. So I'm going to use the second one this time, number 2. F prime of 2 is going to equal the limit as x approaches 2 of f of x minus f of 2 divide by x minus 2. Okay. So now plugging in the actual function, limit as x approaches 2 of 1 over x minus 1 over 2 divide by x minus 2. Okay. We have a complex fraction now, and we need to be able to simplify this complex fraction. Okay, a couple different ways we can do it. One way is to let's focus on the numerator by itself, right? Find a common denominator and simplify the numerator. So common denominator between x and 2 up top, I would need 2x as my denominator, which means the first fraction needs a 2 over 2, and the second fraction needs an x over x. So then I have 2 minus x over 2x in the numerator. Complex fractions are fractions divided by another term. So if I'm dividing by something, I'm also multiplying by its reciprocal. So I can write the division of x minus 2 as multiplication of 1 over x minus 2. Okay? Remember, you're always looking for that indeterminate factor. What's causing the 0 over 0? If I'm inputting in a 2, the corresponding factor that causes the 0 would be x minus 2. So I already have that in the denominator. I need to find it in the numerator, which means I don't want to go and distribute things and FOIL things out and such. We want to stay in factored form. So my denominator is factored form. My numerator is so close to x minus 2, I just need to factor a negative 1 out of there. Okay, so now I've effectively found the x minus 2 top and bottom. Get rid of it. There's that negative up top that I know that I was looking for because I already said that my slope should be negative. So now I can evaluate this limit of negative 1 over 2 times 2, or negative 1 over 4. So there's my slope. That's my f prime at 2. Right, if I want the line, I need my point, I need my slope, and then I can write my equation to a line. My point comes from the original. Without even knowing it, you are finding the ordered pair of the original. Right? I inputted f of 2, and I got out 1/2. So my ordered pair is 2, 1/2. My slope, well, that's the work that I just did. That's negative 1/4. So then my line becomes y minus 1/2 equals negative 1/4 times x minus 2. And that's your final answer. Okay. Now, I'm going to leave this one for you to try. I'm sorry, there's actually 2 here for you to try, and then in class we'll be able to go through it together. And I also, remind me, I also want to go through and prove this one in class. Okay, f prime of a for the linear function f of x equals mx plus b. M and b are constants. So go through this and see if you can do it using the mx plus b, but I want to walk through this together in class. Okay, just as a reminder, this homework that's at the end of the notes may or may not coincide with the actual problem set, but don't do it just because it's right here. Look for the problem set within the modules. Okay, So closure, we're thinking about what is a derivative. So today we looked at it as the limit definition, but we know that it's instantaneous velocity. We know it's a rate of change. How can you find the derivative of a function at a particular value? So you have two different quotients that you can be using, okay, at this point.